just no way around it. So why is it a small fraction? Well, yeah, most of the atmosphere, fortunately for us, is how would you say, diaphanous, transparent to infrared radiation. So the nitrogen and oxygen in our atmosphere that make up the bulk of it don't participate in this energy absorption that John Tyndall showed these other gases do. These gases have to have a certain physical property, and they tend to need to be 3 molecules at least big. 3 atoms, excuse me, large molecules. But the point is that the bulk of the mass in the atmosphere is not what's doing the most important things to this energetic. And so that's why it's not a matter of how many are there, it's a matter of what those that are there are doing. And is there a proportional change that's occurring? And that's definitely the case. Does that answer it? Okay. Yeah.
So it seems like this problem is festooned with a linkage of multiple feedback loops.
Yeah,
which
right.
makes it very difficult to understand.
Yeah. Yeah.
Things that cause into feedback loops like melting ice caps and also permafrost and methane and stuff like that.
Exactly right.
You also mentioned that at least one negative feedback loop, which apparently hasn't been very well validated and tested yet.
Yeah, I mean, work that I've been doing myself kind of shows that there's most of the sulfur, the gas that's emitted by the algae, actually just very rapidly gets dumped back in the ocean through natural processes. So
I'm just wondering if you could just outline for us the top handful of these feedback loops. I mean, there must be many of them, but...
well, there's not a whole lot on the negative side. I gave you positive and negative, but the negative side is more scant.
Okay.
One that, again, people don't think is going to be very strong is that we're producing all these things. Like I said, we're mobilizing nitrogen in terms of fertilizers, and in combustion we make nitrogen oxides. So we're doing that, and that, in principle, can be a limiting nutrient to some forest ecosystems, some terrestrial ecosystems. So in principle, we could be eutrophying the biosphere, if you know those words, stimulating it by dumping in nutrients that weren't there before we got here. Same with CO2. People say all the time, well, it's light. It's what gives us light. We call it latitude, and then they call it poison. Yes, it's very important for this growth. So there's the nitrogen eutrophication or fertilization and CO2 fertilization as well. But everything that's been, the studies that have gone down seriously on those two fronts don't seem to indicate that those are going to be very sustainable or very strong in the long run. That is, the idea being that if you start stimulating the biosphere in one way or another, like with nutrients, it'll start growing more and sucking down more CO2 and storing more carbon in the life on Earth. And so that doesn't seem to be a big one, and that's another the other negative one that I think negative feedback. So did you want more?
Well, I was just wondering if the feedback loop about the albedo and the one about the permafrost methane, are those the two main positive ones, or are there other big ones that we should be looking at?
Well, the water one is huge. So we think Venus at some point may have had an atmosphere something like ours, and may have had oceans. But as it got warmer and warmer and warmer, those oceans boiled off. And what I didn't say, or just elided kind of quickly, is that the greenhouse effect, the strongest component in here is water vapor, which you can't see. It's not a cloud, but water vapor. So as the surface warms up, we know that's going to probably just evaporate more water, right? That's another simple kind of junior high school physics thing. So there's going to be more water vapor at higher temperature. And that's a feedback that's positive and is also a little bit alarming.
So gives you more
water holds the heat, but at the same time it creates more clouds, which also reflects sunlight.
Well, no. So, okay, so I don't like the word, I don't use the words heat and holding and all that, because it's a photon, right? It's light. It's infrared light, and it's absorbed by a molecule. And now that photon's gone. It's not going to redirect it somewhere. It's energy that's now thermal energy of a molecule, the water molecule, and it shares it with all of its neighbors. So yes, water's going to do that, and that's warming the atmosphere. It's also going to radiate more, which is going to radiate down on us and keep us warmer. But the cloud thing is another tricky one. Clouds down low, like these stratocumulus over the ocean here that we know and love so well, these are cooling because they're down low and they're reflecting sunlight. Clouds that are higher, like cirrus, actually work the other way. They work like a greenhouse gas. So they actually warm. So the cloud question is a lot more complicated. It actually depends on where the cloud's out, how long they live, and all that. So that's another fun thing if you're interested in joining the climate science ranks, is studying clouds. We really need to know a lot more about clouds and how they affect. So yeah, I'm sorry, you were saying.
Question. What's your opinion or your thoughts on I mean, obviously we are affecting the atmosphere. What about geoengineering as a mitigation mechanism?
Okay, so my personal feeling, I mean, there's a lot of discussion about this, but I would just bring up again this is the stratospheric ozone problem was what I was kind of leaned on, and this is what I remember thinking like, wow, that's exciting stuff. And at the time, I told you it was incomplete knowledge. We knew it was these halogens in the stratosphere, these chlorine atoms that somehow got liberated and destroyed the ozone. We knew that much. And people said, very smart people now, people at the National Academy of Science reports and so forth, saying that what we can do is fly up there, a bunch of propane tanks, and we release all this propane gas. Pretty inert, not going to do much harm, and we'll just chew up all the chlorine, and then boom, we'll be done. We'll fix it. Fill in the hole. And people are like, well, okay, that's not bad idea. There's some cost, you gotta fly up there, you know, propane. And turns out when the understanding came about that there was on these polar stratospheric clouds, that would have just massively exacerbated the problem. Because we didn't understand the science completely. So like I said, I started out thinking, I know I'm wrong because I'm a scientist. That's the fun part. And the fun part is proving myself wrong, right? But so then to have the moxie to say, well, but I do know that if you put something in the stratosphere, that'll fix it. So I'm a little cautious myself because I know that our knowledge is incomplete. But some proposals are not, seem like, well, the longest they're going to affect us is about a year, so maybe we can do that, and it probably won't have these long consequences. But again, you just don't ever know. So is that sufficient? Yeah.
I know that in the past, through ice courses, that we've seen heating, cooling things. We've certainly gone through ice ages now. Do we know what breaks that feedback loop? So as it gets warmer and warmer and warmer, it breaks and then starts going to ice age. Do we know what breaks that loop?
You mean initially? So it doesn't just keep going down?
We have been in ice ages, we're not in ice age now, and we've been several. So at some point, it got warmer and then turned around and got cold. So
the best idea.
What broke that made go?
Well, the best idea is, as far as I know, is that these orbital parameters of the Earth. So the Earth's orientation with respect to the plane of the sun and its orbit around the sun, these all have little wobbles. Everything on Earth is wobble. And so as it goes around, then in the different phases of that wobble, you have different forcings, solar forcings. And so the idea is that those forcings are what stimulates this change. And this very distinct periodicity of 200,000 years. So, yeah.
With respect to the hole in the ozone layer, to what level have we been successful in fixing that problem? And did that not also contribute to the warming of Antarctica?
Okay. So, well, as far as I know, we think it's getting better, but it's slow. And we knew this was going to be a 50-year thing to fix, roughly speaking. So, the Antarctic, we think, is actually getting better. But it is slow, so we still do see quite a sizable hole, although it's not a complete hole, it's a thinning, right? But the signs do indicate that it's changing, it's going to improve. But that's still not quite, it's not glaring yet at this point. So your other question was ties to warming.
Wasn't that the thinning of the ozone layer there to some extent keeping Antarctica cooler than it would have been?
Well, so when we talk about warming, that's actually all below the stratosphere. Distinctly below it. The surface and the atmosphere, well, the lower part of the atmosphere, I would say. The stratosphere, it turns out, if you dump a bunch of CO2 into the atmosphere, that actually warms the troposphere, the lower part of the atmosphere, and the surface. But it actually turns out, because of the funny way that the system works, is it actually cools the stratosphere.